Hello everyone. Today I'm going to talk about TextCaps dataset and challenge. TextCaps is a dataset for image captioning with reading comprehension. And this is a joint work with folks at Facebook AI Research and Georgia Tech, specifically Yash, Alexi, Rongang, Devi, and Marcus. First, we will talk about the TextCaps dataset and its details. Then we will dive deep inside the challenge analysis and its winners. Let's first take a look at these images and figure out what is common in all of them. Yes, they all contain text. Text is a very important aspect of how we understand and perceive the world around us in our daily life. But surprisingly, text is not an important part of our machine learning applications and dataset as of now. Let's see how a human would caption this image. And now let's see how image captioning sort of model would caption this image. As you can see, the captioning model didn't even include text anywhere inside this description. This is because these captioning models are not even aware of text present inside the image, given that our datasets don't consider them during the annotation process. This is where text caps comes in. For collecting texts, we specifically ask the annotators to use the scene text present inside the images to create a caption. Current dataset have led to a situation where the current captioning models cannot even read, even though text is a very important aspect of our visual world. As you can see in these examples, that the text present in these captions is very random. So we can break down what is needed to successfully describe these images. First is that we need to extract the OCR tokens from these images and then also generate a grammatically correct sentence which combines words from a normal vocabulary with these OCR tokens. This is further accompanied by the problem of figuring out the relationship between different OCR tokens and which OCR tokens go together. Specifically, this is dependent on the semantics and spatial relationship as well as the visual appearance of the OCR tokens. As you can see in these examples, even though the positioning of these OCR tokens are very different, some of them will go together. Also, like you have to switch multiple times during your caption generation between the words from vocabulary as well as the OCR tokens. A lot of the time you have to like paraphrase the information given inside the image to make it useful for the reader. So that is also one of the technical challenge. There is yet another challenge of unseen OCR tokens at test time. Because text in the images can be anything, you can't really map it to a fixed vocabulary. So this challenge also has to be covered. It is unlikely that such capabilities will naturally emerge through supervised training on existing dataset. For this purpose, we created TextCaps. There are 140,000 plus captions for 20K images with text, as you can see some examples inside this image. We also ensure that the reading comprehension is required for the captions inside TextCaps by doing multiple evaluations by asking separate annotators to verify the original annotations. 81% of TextCast caption contain OCR token, whereas this number is only 3% for Coco captions. Text caps also require multi-word reading, whereas 57% of the captions contain two or more tokens. To give an idea of how rare the OCR tokens are, more than 9,000 tokens appear only once in the whole dataset, whereas 50% of the unique OCR tokens appearing in the text caps never have appeared in validation or training set. Hence, they are zero shot. TextVQ and Coco, for 90% of their captions, don't even require switching between fixed vocabulary and OCR. Whereas, as you can see from the plot, most of the text captions require at least two switches between OCR and fixed vocabulary. Let's talk about the baselines that we introduced with the TextCaps dataset. First, we adapted the MFOC model for text VQA to do captioning instead of answer prediction. The MFOC model could already do multi-word answer prediction, so we adapted it to just generate captions. Benchmark with state-of-the-art models such as bottom of top-down and AONet shows that their CIDR score is very low compared to what the human CIDR score is on text caps. Whereas MFOC caption does improve a lot on these baselines, there is still a large gap to complete. Let's take a look at some of the predictions from MFOC caption model. As you saw in the previous images, datasets is indeed the key to like get reading comprehension inside captioning models. We can see that the models trained on Coco in this particular example don't do as well as the models trained on Coco plus TextCaps. Specifically, they add the necessary components of the image to the caption to make it meaningful. Let's talk about this year's challenge results. I would first like to congratulate Microsoft Cognitive Service team for winning this year's challenge. For this year's challenge, we had 101 total submissions on validation and test standard phases combined. We had 6 valid teams on test standard phase. And this year, 3 teams were able to beat the baseline M4C caption. Compared to last year's challenge winner, we have seen a drastic improvement of 20 cider points. And if we compare to a TextCaps original baseline M4C caption that was released 1.5 years ago, we have come a long way. But looking at the human performance, we still have a long way to go. Let's take a look at the qualitative analysis for these models and see what they actually predict. Magic Shuvan is the second team for this year's TextCaps challenge. So the Microsoft entry, the winning entry, was able to figure out that this is actually a car and not a white van as predicted by M4C capture and the second team. Whereas the humans were even more specific with taxi and the number plate in their captions. So we are doing really good compared to what we were doing in M4C captioner. This is a little bit more complex example with a lot going on in the picture. The humans do a good job at capturing it well, whereas most of the models are confused and can't even figure out that these are shoes and not boxes or shells. This is an example that actually requires some reasoning to figure out what is happening. As you can see, the human was able to write a good caption for this, whereas these models are still confused and can't actually give meaningful information as of now. Now let's jump into some quantitative analysis and look at the average length of the captions generated by these models. Surprisingly, compared to M4C Captioner and the humans, that these newer models that are winning entries for this year's challenge usually predict smaller captions. The average number of OCR tokens per captions have gone quite high compared to last year's, which is also surprising but also says that the image captioning with reading comprehension can't really be solved without using OCRs. Even the switches among per caption between the fixed vocabulary and the OCR is quite high for the winning model. To summarize, we introduced TextCaps, a dataset that targets image captioning with reading comprehension and contains 142 per captions. It has technical challenges around understanding OCR and understanding how to switch between OCR and fixed vocabularies to generate reasonable sentences. We saw that the standard captioning models fail on TextCaps, whereas the models which use copy mechanism and OCR show good results. There's still a significant gap to humans, which we hope the community will close within next few years. I once again congratulate the Microsoft team for winning the TextCaps challenge for 2021. While we are here, we also want to introduce TextOCR dataset, which is the newest addition to TextVQ and TextCaps ecosystem. TextOCR aims to benchmark text recognition on arbitrary shaped scene text. It's built on TextVQ and TextCaps images and contains 1 million word annotations, making it the largest scene text dataset available for OCR recognition. We hope that the TextOCR will help bridge the gap between the OCR systems and the downstream applications like TextVQ and TextCaps. Come to our poster session at CVPR 2021 for more details on Wednesday, June 23rd, 11 to 1:30 p.m. Finally, we thank all of the participants for their time and their efforts. The challenge will remain open at Eval AI and the starter code is available inside MMF. Thank you.